Welcome back to recitation. Today what I'd like to do is work on using Riemann sums to approximate definite integrals. So what we're going to do first is I'm going to let you work on the problem. So let me state the problem. I'll give you a little time to work on it, and then I'll come back. So the problem is the following. We want to use 4 subintervals and left endpoints to approximate the following definite integral. The integral from -1 to 3 of the function x cubed. And I've drawn a rough sketch of what x cubed, y equals x cubed looks like to help you out as a starting point. So why don't you use the 4 subintervals and left endpoints to approximate the definite integral? Then I'll come back and show you how I do it. Okay, welcome back. So what we want to do again is use Riemann sums to approximate this definite integral. And I've given you the specifications of 4 subintervals and left endpoints. So I'm going to draw what these 4 subintervals and their left endpoints are going to give us on the graph. Then we're going to calculate what the actual value is of this estimate. And then I'll show you a way you can write it in some different notation. So let me actually find some blue chalk. Excuse me. So using blue chalk, I'm going to show you where the 4 subintervals and the left endpoints. So it's -1 to 3, so I've conveniently done it so we have every unit length as one of the subintervals. They're all unit length. And if I want left endpoints, then my rectangle's heights, if you remember, are going to be the output at the left side of the interval. So I'm going to designate the left interval's outputs. And what do we have here? I'm going to now draw rectangles of those, using those with the one side on the x-axis and one side at the height of the left endpoint's output. So there's one rectangle. Oh, I almost did something wrong here. This left endpoint's rectangle has no height because the left endpoint's value is 0. The output is 0. There's another rectangle, and there's the last rectangle. So to designate everything carefully, I will call this value y0, the output value here y0. This value will be y1. The output value here will be y2. And to show exactly what do I mean by output value, here I have enough room to write the height is really what it is y3. So y0, y1, y2, and y3 designate the heights of these 4 rectangles. And the length of each rectangle, if you remember, is really what we designate as delta x. So this right here is delta x. And in this case, delta x is each time equal to 1. So remember, formally, what we want to do is if we want to find this definite integral, we want to find the area under the curve between the x-axis and the function x cubed. And remember, this is signed area, so anything below the x-axis has a negative sign associated to it. Anything above the x-axis has a positive sign associated to it. So when I'm trying to determine this, when I'm trying to do an estimate, I'm finding the areas of these rectangles. So my first approximation that I've given here is we want the 4 subintervals and the left endpoints. What we really need is this delta x, which is the base, times the height, which is y0, 1, 2, and 3 of each of these rectangles. So to write it carefully, well, I guess this won't be the most careful way we write it, but I have the base, which is delta x in each case, times y0 plus y1 plus y2 plus y3. And the only thing I have to be careful of is that the area of the rectangle here will be negative, but how do I pick that up? I pick that up because this y0 value as an actual output is negative. So that actually will be picked up automatically by the value of the output on the function. So let's evaluate these things. Y0 should be the value of the function at x equal -1. When x is -1, the function, remember, is x cubed, so I get -1 cubed, which is just -1. So delta x is 1. Y0 is -1. Y1 is the value of the function at x equals 0 because my left endpoints are -1, 0, 1, and 2. So the second one is 0 as the input. At x equals 0, I get 0 as an output. The y2 is going to be this third left endpoint. That's at x equal 1, 1 cubed 1 cubed is 1. So I get a 1 there. And then the third left endpoint, I had minus 1, 0, 1, it's 2. So the third left endpoint is 2. 2 cubed is 8. And so y3 is 8. Hopefully the subscripts here didn't confuse you, because I actually was very close to having the subscripts represent the x value. But that's not, in fact, what the subscripts are doing. The subscripts are just representing what interval we're looking at. So the 4 intervals are designated by 0, 1, 2, and 3. So I get, when I put this all together, I get 1 times, well, minus 1 plus 1 is 0. 1 times 8, so I get 8. And if I wanted to look at the picture, how is that represented? Well, this rectangle has base 1 and height 8, so that has area 8. This rectangle is actually a square. It has base 1, height 1. And this one is also a square. It has base 1, height 1, but because it's below, it has a minus sign associated to it when I think about it in terms of area. So I get minus 1 plus 1 plus 8, and that's where the 8 comes from. Now, if I wanted to write this in terms of a Riemann sum, you see them sometimes written in this way. You can think about it. You can think about it in a formal sum in this way. You've probably seen this in the lecture videos more like this. The sum from I equals 0 to 3 of f of x of I delta x. And now, in this case, we could even be more deliberate if we wanted to, and we could let x sub I be designated by some value, we could say, starting at -1 and adding some number to it each time based on the interval. But this is sort of the easiest way to write out what we're interested in. And then the x sub i's are going to be designated separately. We can write x sub 0 is equal to -1, x sub 1 is equal to 0, x sub 2 is equal to, sorry, not -1, is equal to +1, and x sub 3 is equal to 2. So in that case, that's what we would get there. And we could write it in that way and then get the same values. So I think I will stop there.